Hello, in this lecture we will find out the area of the green triangle. In the drawing we have square ABCD. We know that one side of square ABCD equals to 4 units. The length of AD is 4 units, and it equals to DC equals to BC equals to AB, because all the sides of a square are equal to each other, so all the sides they are equal to 4 units. And inside this square ABCD, we have this circle, and we know that the radius of this circle equals to 1 unit, and we want to find out the area of this green triangle. So first of all, I will present to you a new rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. I will repeat on rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and also we have tangent AB, this tangent AB is tangent to this circle at this point. We will define the touching point between tangent AB and the circle as point M. Actually, point M is the point of tangency, of tangent AB with this circle. Suppose that this is the center of this circle. We will define the center of this circle as point O. Then we'll join together points O and M by a straight line. OM is the radius of this circle, and as you can see from the drawing, this radius, the radius OM, is drawn to the point of tangency. That is to say, it is drawn to point M, that is the point of tangency of tangent AB with this circle. Therefore, according to rule number 1, the tangent AB will be perpendicular to this radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So I will read rule number 1 again. A tangent to a circle, that is to say tangent AB, is perpendicular to the radius drawn to its point of tendency. So whenever we have a radius like this radius OM that is drawn to the point of tendency, then the tangent AB will be perpendicular to this radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So that is the meaning of rule number 1. And we actually can implement rule number 1 in our drawing, because first of all, we will define the center of this circle as point O, and we will define the touching point of the point of tendency of tangent AD with this circle as point M. So actually OM is the radius of this circle that equals to 1 unit, R equals to 1. So as you can see in the drawing, we have this radius OM. It is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AD with this circle. Therefore the tangent AD will be perpendicular to this radius. That is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Why? Because this radius, it is drawn to the point of tendency. Whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to this radius. That is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. And we also this angle is 1 out of 4 angles inside square ABCD, and we know that all the angles inside a square are right angles. Therefore this angle is a right angle, that is to say it equals to 90 degrees. We will define the point of tendency of tangent AB with this circle as point N. Then we will join together points O and N by a straight line. Actually ON is the radius of this circle, because of the fact that line segment ON starts from the center of the circle, that is to say from point O, and ends at point N, that is a point on the circle itself. Therefore that is exactly the definition of the radius. It is the radius of this circle that equals to 1 unit. And again, we have the radius ON is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent AB with this circle. Therefore the tangent AB will be perpendicular to this radius, that is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay. In the next step, we will define the point of tendency of tangent CE with this circle as point K. Point K is the point of tendency of tangent CE with this circle. Then we will join together points O and K by a straight line. Actually OK, this line segment OK, is also the radius of this circle, because of the fact that line segment OK starts from point O, that is the center of the circle, and ends at point K, that is a point on the circle itself. Therefore OK is the radius of this circle that equals to 1 unit. And again, we have this radius, the radius OK is drawn to the point of tangency, that is to say it is drawn to point K, that is the point of tangency of tangent EC with this circle. Therefore, according to rule number 1, the tangent AC will be perpendicular to this radius. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay. In the next step, I will present to you a new rule. Rule number 2. According to rule number 2, the sum of the angles in any quadrilateral is equal to 360 degrees. The sum of the angles in any quadrilateral is equal to 360 degrees. I will read rule number 2 again. According to rule number 2, the sum of the angles in any quadrilateral is equal to 360 degrees. So, we'll focus on quadrilateral MOAN. And we know that the sum of the angles in quadrilateral MOAN, this quadrilateral, is equal to 360 degrees according to rule number 2. So, which angles we have in quadrilateral MOAN? We have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of this angle that we will define as angle X. So the sum of those 4 angles must be equal to 360 degrees according to rule number 2. So I'll repeat again. The sum of the angles in quadrilateral MOAN must be equal to 360 degrees according to rule number 2. So we have in quadrilateral MOAN 3 right angles. The sum of the 3 right angles is 270 degrees plus the size of the 4th angle. In total, those 4 angles must be equal to 360 degrees according to rule number 2. Here we will subtract 270 degrees from this equality, and we will get that angle X equals to 360 degrees minus 270 degrees, it equals to 90 degrees. So we actually found out that angle X is a right angle, it equals to 90 degrees. So we can substitute X by a right angle. So as you can see, all 4 angles inside quadrilateral MOAN are right angles. They are all equal to 90 degrees. And we also have rule number 3. According to rule number 3, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So I'll write it down. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So if not a square, it must be a rectangle. So either it will be a rectangle or square. So at least it is a rectangle. So I will read rule number 3 again. According to rule number 3, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. And actually, our quadrilateral MOAN has 4 right angles. Therefore, according to rule number 3, quadrilateral MOAN is a rectangle. So we will relate to quadrilateral MOAN as a rectangle. Okay, so according to rule number 3, quadrilateral MOAN is a rectangle, so we will relate to it as a rectangle. Okay, quadrilateral MOAN is a rectangle according to rule number 3 because it has 4 right angles. Okay, and we also have rule number 4. According to rule number 4, the opposite sides of a rectangle are equal to each other. So I will read rule number 4 again. According to rule number 4, the opposite sides of a rectangle are equal to each other, and actually we will relate to quadrilateral MOAN as a rectangle. Therefore, the opposite sides of rectangle MOAN are equal to each other according to rule number 4. That is to say, if we relate to rectangle MOAN, its opposite sides are equal to each other according to rule number 4. That is to say, MO equals to AN, I will repeat again. In rectangle MOAN, according to rule number 4, its opposite sides are equal to each other. That is to say, MO equals to AN. Okay? But we know that MO equals to 1 unit. It is given us in the question. So we can write here that MO equals to 1 unit, and from this equality we will conclude that AN also equals to 1 unit. Okay? AN also equals to 1 unit. So we can write here that AN equals to 1 unit. Likewise, according to rule number 4, MA equals to ON. Again, MA equals to ON according to rule number 4, that the opposite sides of a rectangle are equal to each other. But we know, we have already found out that ON equals to 1 unit. So we can write here that ON equals to 1 unit. And from this equality, we will conclude that MA also equals to 1 unit. MA also equals to 1 unit. So we can write here that MA equals to 1 unit. So you can see here that all 4 sides of quadrilateral MOAN, they are equal to each other and they are all equal to 1 unit. And quadrilateral MOAN has also 4 right angles. And we also have rule number 5. According to rule number 5, if a quadrilateral has 4 right angles and 4 equal sides, then it is a square. So I will repeat on rule number 5 again. According to rule number 5, if a quadrilateral has 4 right angles and 4 equal sides, then it is a square. And as I already showed you, quadrilateral MOAN has 4 equal sides and 4 right angles. Therefore, quadrilateral MOAN is a square according to rule number 5. So I will write it down. Quadrilateral MOAN is a square according to rule number 5 because of the fact that it has 4 right angles and 4 equal sides. Okay, quadrilateral MOAN is a square. And we also have rule number 6. According to rule number 6, the diagonals of a square bisect the angle of the square, bisect the angles of a square into 45 degrees angles. I will repeat on rule number 6 again. According to rule number 6, the diagonals of a square bisects the angles of a square into 45 degrees angles. So what is the meaning of rule number 6? The meaning of rule number 6 is that if we relate to square MOAN, then its diagonal OA the diagonal OA of square MOAN bisects this angle into two angles of 45 degrees. This is the right angle, and the diagonal OA bisects the right angle into two angles of 45 degrees. So, according to rule number 6, this angle will be equal to 45 degrees, and this angle will be also equal to 45 degrees. So, actually, this angle equals to 45 degrees according to rule number 6. So, that is to say, angle OAN equals to 45 degrees according to rule number 6. But we can relate to this angle that equals to 45 degrees also as angle OAB. Why we can relate to it as angle OAB? Because of the fact that points N, B, and A are all located on the same straight line. Therefore, it doesn't matter at all if we call to this angle that equals to 45 degrees angle OAN or angle OAB, because of the fact that those two points N and points B, are located on the same straight line. It will not change anything if we relate to this angle that equals to 45 degrees as angle OAB, or if we relate to it as angle OAN. The length of the angle will still remain 45 degrees. So we can write down that angle OAB equals to 45 degrees according to rule number 6. So in quadrilateral, in square MOAN, this angle OAB, equals to 45 degrees according to rule number 6, that the diagonal OA bisects this angle A, to two angles of 45 degrees. Likewise, if we relate to the big square ABCD, according to rule number 6, the diagonal CA bisect the same angle into two angles of 45 degrees. So we draw the diagonal CA. Okay, according to rule number 6, the diagonal CA of square ABCD bisects this angle A, into two angles of 45 degrees. So this angle equals to 45 degrees and this angle also equals to 45 degrees. So we can write down that angle CAB, this angle equals to 45 degrees according to rule number 6. So angle CAB equals to 45 degrees according to rule number 6. And angle OAB equals to 45 degrees also according to rule number 6. So here we have two angles. Those two angles, angle OAB and angle CAB, are both equal to 45 degrees. Therefore, they are equal to each other, of course. So we can write down that angle OAB equals to angle CAB. Angle OAB equals to angle CAB. And from the fact that angle OAB, this angle equals to angle CAB, we will conclude that diagonal CA passes through point O. Diagonal CA of square ABCD must pass through point O, otherwise it is impossible that angle CAB will be equal to angle OAB. They will be never equal to each other if diagonal CA will not pass through point O. So our conclusion from this equality will be that the diagonal CA of square ABCD passes through point O. So I'll read it again. Because of the fact that angle OAB equals to angle CAB, we will conclude that the diagonal CA of square ABCD passes through point O. Okay? Otherwise, the angle CAB will not be equal to angle OAB. Okay? So, in the next step, I will present to you a new rule, rule number 7. According to rule number 7, the length of a diagonal of a square is equal to square root of 2 multiplied by the length of each side. I will repeat again on rule number 7, then I will explain it. According to rule number 7, the length of a diagonal of a square is equal to square root of 2 multiplied by the length of each side. Okay, so what is the meaning of rule number 7? The meaning of rule number 7 is that if we have square ABCD, so this is square ABCD, and we know that the length of its sides is equal to S units, so all the lengths of diagonal of the sides of diagonal of a square ABCD are as the length of S units. So if we know that the length of one side of square ABCD is S units, then the length of its diagonals, that is to say BC and AD, the length of diagonal BC of square ABCD will be equal to square root of 2 times S units. Okay, so if we know that the length of one side of square ABCD is S units, then the length of its diagonal or diagonals BC and AD will be equal to square root of 2 times S units. Okay, so we can implement rule number 7 in our drawing because we have square MOAN. In square MOAN, the length of diagonal OA, according to rule number 7, will be equal to the length of the square side, that is to say it will be equal to 1 times square root of 2 units. Okay, I'll repeat again. In square MOAN, the length of its diagonal OA will be equal to the length of the square sides, that is 1 unit, times square root of 2. 1 times square root of 2 is square root of 2. So we found out that OA equals to square root of 2 units. OA equals to square root of 2 units. And if we focus on square ABCD, then the length of diagonal CA and also BD, according to rule number 7, will be equal to the length of square ABCD sides, and the length of one side of square ABCD is equal to 4 4 units. It is given us in the question. So it is 4 times square root of 2 units. So CA equals to 4 times square root of 2 units. So we can write here that the length of diagonal OA of square MOAN equals to square root of 2 units, and the length of diagonal AC of square ABCD equals to 4 times square root of 2 units. So, and what is the length of line segment CO? The length of line segment CO, it is very simple. It equals to CA. It equals to CA minus OA. Again, CA minus OA equals to CO. Very simple. CA minus CO, CA minus AO equals to CO. CA minus OA equals to CO. CA minus OA equals to CO. You can see it from the drawing. So CO equals to CA, and we've already found out that CA equals to 4 times square root of 2 units minus AO. AO equals to square root of 2 units. So 4 times square root of 2 units minus 1 times square root of 2 units equals to 3 times square root of 2 units. So we found out that the length of line segment CO equals to 3 times square root of 2 units. So we can write here that CO equals to 3 times square root of 2 units. Okay? So in the next step, we will focus on the right triangle, triangle COK, on the right blue triangle, triangle COK, so on this right blue triangle, triangle COK, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green and the blue right triangle is CO. So the square of the hypotenuse is CO squared. And it equals to the sum of the squares of the perpendiculars. That is to say, it equals to OK squared plus CK squared. This is CK squared. So in the right triangle, triangle COK, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is CO, therefore the square of the hypotenuse is CO square, and it equals to the sum of the squares of the perpendiculars, that is to say it equals to OK square plus CK square. But we have already found out that CO equals to 3 times square root of 2 units. So CO square will be equal to 3 times square root of 2 square, and it equals to OK square. OK equals to 1, so OK square is 1 square is 1, plus CK square. CK square is the missing variable, so we will leave it as it is. So in conclusion, we found out that CO square is 3 times square root of 2 square, and it equals to 1 plus CK square. 3 times square root of 2 square is 9 times 2, so I'll write it down. Nine times 2 equals to 1 plus CK square. So here 9 times 2 is 18. I'll write it down. 18 equals to 1 plus CK square. We will subtract 1 from this equation, equation number 2, and we get that 18 minus 1 is 17. 17 equals to CK square. Here we'll take a root out of this equation, equation number 2, and we will get that CK equals to the square root of 17 units. So we can write here that CK, this side of the blue right triangle, equals to square root of 17 units. So in the next step I will present to you a new rule, the last rule, rule number 8. According to rule number 8, the lengths of two tangents from a common external point to a circle are equal. I'll read rule number 8 again. According to rule number 8, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 8? The meaning of rule number 8 is that if you have this circle and we have this external point, point P, so why point P is an external point in relation to this circle? Because of the fact that point P is not located inside this circle, nor on this circle, but it is located outside this circle, therefore It is defined as an external point in relation to this circle. So if from the external point P we will draw two tangents to this circle, this will be the first tangent. We will define the point of tendency of the first tangent with this circle as point A, and then we will draw second tangent from the external point P. It is actually common external point because it belongs to two tangents. So we draw the second tangent to this circle, and we will define from point P, and we will define the point of tendency of the second tangent with this circle as point B. Then actually the length of the first tangent is PA, and the length of the second tangent is PB, and according to rule number 8, the lengths of two tangents from a common external point to a circle are equal. So whenever you draw from a common external point, like here from point P, two tangents to a circle, then the length of those two tangents will be equal to each other. That is to say, PA equals to PB. Okay, so whenever you draw two tangents to a circle from a common external point to that circle, then the length of those two tangents will be equal to each other. In this case, PA equals to PB. And PA equals to PB. We can implement rule number 8 in our drawing, because in our drawing we have the external point E. It is external point in relation to this circle. And from point E we have two tangents to this circle. The first tangent is tangent NE, and the second tangent is tangent EK. And according to rule number 8, those two tangents that exist from the external point E to that circle, to this circle, will be equal to each other. That is to say, NE equals to EK according to rule number 8 again. NE equals to EK according to rule number 8, because we have two tangents from a common external point E to this circle, therefore they are equal to each other according to rule number 8. So if we define tangent NE as x, if tangent NE equals to x, then from this equality we will conclude that EK also equals to x. So here EK also equals to x. In the next step, we will calculate the length of line segment EB. Okay, so EB, it equals to, from the drawing you can see that EB equals to AB minus AN minus NA. I repeat again, line segment EB equals to AB minus AN minus NA. It is very simple to see it from the drawing. If you subtract from AB line segment AN and also line segment NE, you will get EB. Okay, so EB equals to AB minus AN minus NE, And we know that the length of AB, it is one side of square ABCD, it equals to 4 units. AN equals to 1 unit. And NE equals to X according to our definition. So in conclusion, we actually found out that EB equals to 4 minus 1 minus X. 4 minus 1 is 3. So in conclusion, we found out that EB equals to 3 minus X. EB equals to 3 minus X. So we can write here that EB equals to 3 minus X. Okay, EB equals to 3 minus X. And we also know that BC is one side of square ABCD, and all the sides of square ABCD equals to 4 units. Therefore, BC equals to 4 units. And we have already found out that CE equals to square root of 17 plus X. So we will implement the Pythagoras theorem on this green triangle. This green triangle is a right triangle. Why the green triangle is a right triangle? Because this angle is 1 out of 4 angles of square ABCD, and we know that all the squares are right angles. All 4 squares of any square are right angles, therefore this angle equals to 90 degrees. So we will focus on the right green triangle, triangle EBC, and we will implement the Pythagoras theorem on the right green triangle, triangle EBC. So according to the Pythagoras theorem, in the right triangle, triangle EBC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So if we relate to the right green triangle, triangle EBC, the hypotenuse in the right green triangle, triangle EBC, it is actually CE, therefore the square of the hypotenuse is CE squared. And it equals to the sum of the squares of the perpendiculars. That is to say, it equals to EB squared plus BC squared. So I'll repeat again. On the right green triangle, triangle EBC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in triangle EBC, in the right triangle EBC, is CE, therefore the square of the hypotenuse is CE squared, and it equals to the sum of the squares of the perpendiculars. That is to say, it equals to EB squared plus BC squared. But we have already found out that CE equals to square root of 17 plus X. So CE squared will be equal to square root of 17 plus X squared, and it equals to EB squared. EB equals to 3 minus X, therefore EB squared will be equal to 3 minus X squared plus BC square. BC equals to 4 units, so BC square is 4 square. 4 square is 16. So in conclusion, we found out that square root of 17 plus x squared equals to 3 minus x squared plus 16 according to the Pythagoras theorem. We will open the brackets in both sides of equation number 3 and we will get that square root of 17 plus x squared equals to 17 plus x squared plus 2 times square root of 17 x, and it equals to 3 minus x squared is 9 plus x squared minus 6x plus 16. So here we have x squared in both sides of equation number 3. So x squared will get cancelled. And 9 plus 16 is 25. So here we will have 25 minus 6x, and on the other side of equation number 1 we have 17 of equation number 3, we have 17 plus 2 times square root of 17x. So here we will subtract 17 from this equation, equation number 3. So 17 minus 17 is 0. We left here only with 2 times square root of 17x, and it equals to 25 minus 17 is 8 minus 6x. So here we will divide the equation number 3 by 2 and we will get that 2 over 2 is 1. So here we have square root of 17x equals to 8 over 2 is 4 minus 3x over 2 is 6x over 2 equals to 3x. So in conclusion, we got that according to equation number 3, square root of 17x equals to 4 minus 3x. Here we will add 3x to this equation, equation number 3, and we will get that square root of 17x plus 3x equals to 4. So in conclusion, we got that according to equation number 3, square root of 17x plus 3x equals to 4. Here we will take out a common factor from those two expressions, and we will take x as a common factor of those two expressions, and we will get that x is a common factor. So what is left from square root of 17x after we took x as a common factor from it? What is left is square root of 17. And what is left from 3x after we took x as a common factor from it? What is left? It is actually 3, and it equals to 4. Here we will divide the equation number 3 by square root of 17 plus 3, and we will get that x equals to 4 over square root of 17 plus 3. Here we will multiply this side of equation number 3 by square root of 17 minus 3, and then we will divide it by square root of 17 minus 3 in order to get rid from square root in the denominator. And we will get that x equals to 4, we will multiply it by square root of 17 minus 3, and then we will divide it by square root of 17 minus 3. And here we have square root of 17 plus 3. So we got this expression after we multiplied this expression by square root of 17 minus 3, and then we divide it by square root of 17 minus 3. We will find out the value of this expression by the following algebraic identity, that a plus b times a minus b equals to a squared minus b squared. Here, in our specific case, a equals to square root of 17 and b equals to 3. So a square, a plus b times a minus b equals to a square. A is square root of 17, so a square is 17 minus b square. B is 3, so b square is 9, so it is minus 9. So in the denominator we will have 17 minus 9, and here we have also 4 times square root of 17 minus 3, it equals to x. So we found out that according to equation number 3, x equals to 4 times square root of 17 minus 3 over 17 minus 9. 17 minus 9 is 8, so we write it down, and we will get that according to equation number 3, x equals, in the denominator we have 8 because 17 minus 9 is 8, and in the numerator we have 4 times square root of 17 minus 3. So in conclusion, we got that x equals to 4 times square root of 17 minus 3 over 8. We will divide this side of equation number 3 by 4. We will divide the numerator by 4, and also the denominator we will divide by 4. We will get that 4 over 4 is 1, so 4 will get cancelled, and 8 over 4 is 2. So in conclusion, we will get that x equals to 4 over 4 is 1, so in the numerator we left only with square root of 17 minus 3. In the denominator we have 8 over 4 is 2. So in conclusion, we found out that x equals, according to equation number 3, x equals to square root of 17 minus 3 over 2. And what is the area of the green triangle, the green right triangle? We have the formula for the area of any triangle. Actually, this is the sign of the area. So the area of any triangle is equal to the base of the triangle times the height over 2. This is the formula for the area of any triangle. It equals to the base times the height to the base over 2. This is the area of any triangle. So in our specific case, the area of the green right triangle, triangle EBC, will be equal, according to this formula, the area of triangle EBC. This is the sign of the area. It means the area of triangle EBC equals to the base of the triangle EBC, that is actually EB, times the height to the base. The height creates 90 degrees with the base, so BC is the height. It creates 90 degrees with the base, EB, over 2. Okay, so EB, the area of triangle EBC equals to EB times BC over 2. Turning to equation number 3. What is actually equation number 4? Turning to equation number 4. The area of triangle EBC equals to EB. EB equals to 3 minus x times BC. BC equals to 4 over 2. So in conclusion, we found out that the area of the green right triangle EBC equals to 3 minus x times 4 over 2. 4 over 2 is 2. 4 over 2 is 2. So we will get that the area of the green right triangle ABC equals to 2 times 3 minus x. According to equation number 4, the area of the green right triangle ABC equals to 2 times 3 minus x. And we have already found out, according to equation number 3, the value of x. It is actually equals to square root of 17 minus 3 over 2. We found out that x equals to square root of 17 minus 3 over 2. So here we will place the value of x from equation number 3 in x from equation number 4 here, and we will get that the area of the green right triangle ABC according to equation number 4 will be equal to 2 times 3 minus x, and x according to equation number 3 equals to square root of 17 minus 3 over 2. Okay, so we place the value of x inside equation number 4, and we got this expression. Here we will multiply 3 by 2, and then we will divide it by 2 in order to have a common factor with this expression. And we will get that according to equation number 4, the area of the right green triangle EBC equals to 3 times 2 is 6 minus square root of 17 minus 3 over 2. Okay, in conclusion, we got this equation number 4. Here 2 over 2 is 1, so 2 will get cancelled. And what is left from equation number 4 after we cancel 2? What is left? It is actually, according to equation number 4, we got that the area of the green right triangle ABC equals to 6 minus square root of 17 minus 3 . So here we will open the brackets here. We got that the area of the green right triangle ABC equals to 6 minus square root of 17 minus 3. Here we will open the brackets of this equation number 4, and we will get that the area of the green right triangle EBC equals to 6 minus square root of 17 plus 3. So in conclusion, we got that the area of the green right triangle ABC equals to 6 plus 3 is 9 minus square root of 17 square units. Or in terms of numbers, the area of the green right triangle EBC equals to 4.88 square units. I will repeat again. We found out that the area of the green right triangle EBC equals to either 9 minus square root of 17 square units, or in terms of numbers, the area of the green right triangle EBC equals to 4.88 square units. I will repeat again. The area of this green right triangle EBC equals to either 9 minus square root of 17 square units, or in terms of numbers, the area of this green right triangle equals to 4.88 square units. Okay? So now I will summarize the lecture. Actually, we wanted to find out the area of this green right triangle EBC, and we have here square ABCD, and we know that the length of one side of square ABCD equals to 4 units. The radius of the circle that is inside the square is equal to 1 unit, and we want to find out the area of the green right triangle EBC. We have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? According to rule number 1, if we have this circle and we have tangent AB is tangent to this circle at point M is the point of tangency, then we have this radius OM, it is drawn to the point of tangency, that is to say it is drawn to point M, that is the point of tangency of tangent AB with this circle. So whenever you have a radius like in this drawing that is drawn to the point of tangency, then the tangent AB will be perpendicular to this radius. That is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. So a tangent to a circle, that is to say AB is perpendicular to the radius drawn to its point of tangency. This radius OM, it is drawn to the point of tangency, therefore the tangent AB will be perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so we can implement rule number 1 in our drawing. We have in our drawing this radius, the radius OM, it is drawn to the point of tangency, that is to say it is drawn to point M, that is the point of tangency of tangent AB with this circle, therefore the tangent AB will be perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. And we know that all the angles inside the square are right angles, therefore this is one angle out of 4 angles of square ABCD, therefore it equals to 90 degrees. And also we have this radius that is drawn to the point of tangency, therefore this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We join points O and N, O and K by a straight line, and we have this radius OK, it is drawn to the point of tangency, that is to say it is drawn to point K, that is the point of tangency E with this circle, therefore the tangent CE will be perpendicular to this radius, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees. Okay, so in the next step I presented to you rule number 2. According to rule number 2, the sum of the angles in any quadrilateral is equal to 360 degrees. So if we focus on quadrilateral MOAN, we know that according to rule number 2, the sum of its angles must be equal to 360 degrees. Which angles quadrilateral MOAN has? It has 3 right angles, 1, 2, 3, and the sum of 3 right angles is 270 degrees. Plus the size of this angle that we define as angle x must be equal to 360 degrees according to rule number 2. So in quadrilateral MOAN, the sum of 3 angles is 270 degrees plus the size of the 4th angle. In total, those 4 angles must be equal to 360 degrees according to rule number 2. We subtracted 270 degrees from this equality and we got that angle x equals to 90 degrees. So we found out that this angle is a right angle, that is to say it equals to 90 degrees. So we have in quadrilateral MOAN 4 right angles. And we have rule number 3 that states that any quadrilateral that has 4 right angles must be at least a rectangle if not a square. And quadrilateral MOAN has 4 right angles, therefore we will relate to quadrilateral MOAN as a rectangle. Okay, we will relate to quadrilateral MOAN as a rectangle according to rule number 3. And we have also rule number 4 that the opposite sides of a rectangle are equal to each other. So in rectangle MOAN, the opposite sides of this rectangle are equal to each other. That is to say MO equals to AN, according to rule number 4. MO equals to AN, but we have already know that MO equals to 1. So from this equality we will conclude that AN also equals to 1. So here AN also equals to 1. Likewise, MA must be equal to ON according to rule number 4. MA equals to ON, but we know that ON equals to 1. So ON equals to 1. So from this equality we will conclude that MA also equals to 1. MA equals to 1. So we found out that all 4 sides of quadrilateral MOAN are equal to each other. They are all equal to 1 unit. And also all 4 angles of quadrilateral MOAN also are right angles. And we also have rule number 5. According to rule number 5, if a quadrilateral has 4 right angles, then it is a square. So therefore, the quadrilateral MOAN that has 4 right angles and 4 equal sides is a rectangle. This quadrilateral MOAN is a rectangle according to rule number 5. And we also have rule number 6, that the diagonals of a square bisects the angles of a square into 45 degrees angles. So here we have square MOAN, and according to rule number 6, the diagonal OA bisects this angle, angle A, into 2 angles of 45 degrees. That is to say this angle equals to 45 degrees and this angle also equals to 45 degrees according to rule number 6. And that is to say angle OAN equals to 45 degrees according to rule number 6. But because of the fact that point A is located on AB, it means that all 3 points A and B are located on the same straight line. Therefore, it doesn't matter at all if we relate to this angle that equals to 45 degrees as angle OAN, or if we relate to this angle as angle OAB, because of the fact that angle N is located on the same straight line on AB. Points A, N, and B are located on the same straight line, therefore it doesn't matter at all if we relate to this angle as angle OAN or relate to it as angle OAB. So we relate to this angle that equals to 45 degrees as angle OAB. So according to rule number 6, angle OAB equals to 45 degrees. Likewise, in square ABCD, we have this diagonal CA bisects this angle, the same angle, into two angles of 45 degrees. That is to say, this angle equals to 45 degrees, and this angle also equals to 45 degrees. So, therefore, according to rule number 6, angle CAB also equals to 45 degrees, because ABCD is a square and CA is a diagonal. Therefore, the diagonal CA bisects this angle into angles to 45 degrees. That is to say, angle CAB equals to 45 degrees according to rule number 6. So angle CAB also equals to 45 degrees according to rule number 6. So we have two angles that are both equal to 45 degrees, therefore they are equal to each other. So we found out that angle OAB equals to angle CAB, and from the fact that angle OAB equals to angle CAB, we will conclude that the diagonal CA must pass through point O. Diagonal CA passes through point O, otherwise angle CAB will never be equal to angle OAB. Okay, our conclusion is that the diagonal CA of square ABCD passes through point O, otherwise angle CAB will never be equal to angle OAB. Then I presented to you rule number 7. According to rule number 7, the length of a diagonal of a square, the length of a diagonal of a square is equal to square root of 2 multiplied by the length of its sides. So what is the meaning of rule number 7? The meaning of rule number 7 is that if we have this square ABCD, and we know that the length of one side of square ABCD equals to S units, then the length of its diagonal BC or AD will be equal to square root of 2 times S units. Okay? We can implement rule number 7 in our drawing, because in our drawing we have square MOAN, its diagonal is OA, and according to rule number 7, the length of diagonal OA will be equal to the length of square OMAN side, that is actually 1 times square root of 2 units. So OA, diagonal OA equals to 1 times square root of 2 units, that is actually square root of 2 units. So OA equals to square root of 2 units according to rule number 7. Likewise, in square ABCD, we know that one side equals to 4 units. Therefore, the length of diagonal CA will be equal to 4 times square root of 2 units according to rule number 7. So CA, diagonal CA in square ABCD will be equal to 4 times square root of 2 units. So we found out that OA equals to square root of 2 units and CA equals to 4 times square root of 2 units according to rule number 7. And we found out the value of CO. CO equals to CA minus OA. Again, CA minus OA equals to CO. That is to say, CO equals to CA minus OA, but we know that CA equals to 4 times square root of 2, and OA equals to square root of 2. In conclusion, we found out that CO equals to 4 times 2 units minus 4 times 2, 4 times square root of 2 units minus square root of 2 units. That is to say, CO equals to 3 times square root of 2 units. So CO equals to 3 times square root of 2 units. And then we focused on the right triangle, triangle COK. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is CO, so the square of the hypotenuse is CO square, and it equals to OK square plus CK square. CO equals to 3 times square root of 2. Therefore, CO square will be equal to 3 times square root of 2 square. And it equals to OK square. OK equals to 1, so OK square is 1 square, 1 square is 1, plus CK square. 3 times square root of 2 square is 9 times 2, and it equals to 1 plus CK square. 9 times 2 is 18, 18 equals to 1 plus CK square. We subtracted 1 from this equality, equation number 2, when we got that 18 minus 1 is 17, 17 equals to CK square. We took a root out of this equality, equation number 2, and we found out that CK equals to square root of 17 units. Ck equals to square root of 17 units. Then I presented to you rule number 8. According to rule number 8, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 8? The meaning of rule number 8 is that if we have a common external point, point P, and from point P we will draw two tangents to this circle, then the length of those two tangents will be equal to each other. That is to say, PA equals to PB. And we can implement rule number 8 in our drawing because we have the external point, point E, and from the external point, point E, we have two tangents to this circle. Therefore, according to rule number 8, they will be equal to each other. That is to say, En equals to Ek. En equals to Ek according to rule number 8. If we define En as x, then from this equality we will conclude that Ek also equals to x. So we got that En equals to x and Ek equals to x2. And then we calculated the value of EB. The value of line segment EB equals to AB minus AN minus EN. That is to say, it equals to AB. EB equals to AB minus AN minus EN. AB is 4, AN is 1, and EN is x. So in conclusion, we found out that EB equals to 3 minus x. EB equals to 3 minus x. And we know that BC equals to 4 units, and CE equals to square root of 17 plus x. So we focused, and we know that the green triangle is a right triangle because this angle is 1 out of 4 angles of square ABCD, and all angles of square ABCD are right angles, and this angle, it is also a right angle. We implemented the Pythagoras theorem on the green right triangle, triangle CEB. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is CE, so the square of the hypotenuse is CE square, and it equals to EB square plus BC square. CE equals to square root of 17 plus x, so CE square equals to square root of 17 plus x square, and EB equals to 3 minus x, so EB square will be equal to 3 minus x square. BC equals to 4, so BC square is 4 square, 4 square is 16. So we open the brackets on both sides of the equation, and we got that this expression here, we cancelled, we have x square on both sides of the equation, so x square will get cancelled. And we also know that 9 plus 16 is 25. So in conclusion, we got that 17 plus 2 times square root of 17x equals to 25 minus 6x. Here we subtracted 17 from this equation, equation number 3. And we got here 2 times square root of 17x equals to 25 minus 17 is 8. So we got that 25 times square root of 17x equals to 8 minus 6x. We divided this equation by 2, and we got that square root of 17x equals to 4 over 2 is 8 over 2 is 4, and minus 6 over 2 is minus 3x. So in conclusion, we got that minus 17x equals to 4 minus 3x. We added 3x to this equation, equation number 3, and we found out that square root of 17x equals square root of 17x plus 3x equals to 4. Here we took a common factor x from this expression, and we got that x times square root of 17 plus 3 equals to 4. We divided this equation by square root of 17 plus 3, and we got that x equals to 4 over square root of 17 plus 3. Here we multiplied this side of the equation by square root of 17 minus 3, and then we divide it by square root of 17 over 3, and we've solved this expression according to the algebraic identity that a plus b times a minus b equals to a square minus b square. So in the denominator we have 17 minus 9, and in the numerator we have 4 times square root of 17 minus 3. 17 minus 9 is 8. So in conclusion, we got that x equals to 4 times square root of 17 minus 3 over 8. We divided this side of the equation by 4. 4 over 4 is 1, and 8 over 4 is 2. So in conclusion, we got that x equals to square root of 17 minus 3 over 2. and we know that the area of any triangle equals to the base of the triangle times the height to the base over 2, and the green right triangle, triangle EBC, the base is EB, the height is BC, so the area of the green right triangle, triangle EBC equals to EB times BC over 2, and we know that EB equals to 3 minus x and BC equals to 4 units, so in conclusion we got that the area of the green right triangle EBC equals to 3 minus x times 4 over 2. 4 over 2 is 2, so in conclusion we got the area of the green right triangle, triangle EBC equals to 2 times 3 minus x. And we already found out that the value of x, according to equation number 3, equals to square root of 17 minus 3 over 2. So we placed the value of x from this equation, equation number 3, in equation number 4. And we got that the area of the green right triangle, triangle EBC equals to 2 times 3 minus, this is x actually, and then we multiplied 3 by 2 and then we divided by 2 in order to have a common factor with this expression, and we got that the area of the green right triangle, triangle EBC equals to 2 times 6 minus square root of 17 minus 3 over 2. 2 over 2 is 1, so 2 will get cancelled, and in conclusion we got that the area of the green right triangle, triangle EBC equals to 6 minus 17 minus 3. We open the brackets on this equation, equation number 4, and we got that the area of the green right triangle, triangle EBC equals to 6 minus square root of 17 plus 3. So we got that the area of the green right triangle, triangle EBC equals to 6 plus 3 is 9 minus square root of 17 units. So the area of the green right triangle equals to either 9 minus square root of 17 units, so in terms of numbers, the area of the green right triangle equals to 4.88 square units. I will repeat again, the area of this green right triangle, triangle EBC equals to either 9 minus square root of 17 square units, or in terms of numbers, the area of this green right triangle, triangle EBC equals to 4.88 square units. Okay, thank you very much.